Hello students, and welcome to section 7-7, Solving Radical Equations and Inequalities. Today we're going to go ahead and take a look at solving radical equations, and the following steps are used in solving equations that have variables in the radicand. Some algebraic procedures may be needed before you use these steps. Step 1. Isolate the radical on one side of the equation. Step 2. To eliminate the radical, raise each side of the equation to a power equal to the index of the radical. Step 3. Solve the resulting equation. And step 4. Check your solution in the original equation to make sure that you have not obtained any extraneous solutions. Okay, so let's take a look. For example 1, it says solve 2 times the square root of 4x plus 8, and then minus 4 equals 8. So again, step 1, isolate the radical, which they'll do by adding 4 to each side to get 12, and then dividing by 2 in the next step, such that you now have the square root of 4x plus 8 equals 6. Next, step 2. To eliminate the radical, raise each side of the equation to a power equal to the index of the radical. The index here, if you remember, is 2 because it's a square root. So if we square both sides, it ends up simply now being 4x plus 8, and of course 6 squared, 36. Next, subtract 8, because you're going to be solving in step 3. Subtract 8, 28, divide by 4, and there you have x equals 7. Step 4 is actually more important than you could imagine here, checking your solution. And the reason is because you may have something called extraneous roots. In other words, solutions that technically don't work. That may happen on these. So, to check, we simply plug in 7 into the original problem for x. So we have 2 times the square root of 4 times 7 plus 8, which of course, if you do that, becomes 36. Minus 4, and yes, it hopefully should equal 8 in the end. We'll see. 2 times the square root of 36 minus 4 equals 8. Still a question mark here. The square root of 36 is 6. In other words, 12 minus 4 is 8. So this question mark is technically a check, I would say, in that it works. So 8 equals 8. X, therefore, is equal to 7. Example 2. Solve square root of 3x plus 1 equals the square root of 5x, and then minus 1 outside that root. Right away, you are actually looking at step 1 already technically done for you. So we're going to jump to step 2. So you're going to square both sides. Now it's going to be a little bit different where if you square this, you're going to have technically some foiling to do, but that's nonetheless necessary. So if you square this left side, it becomes simply 3x plus 1. But if you square this, like I said a moment ago, these are going to have to be what you FOIL. The square root of 5x minus 1, there it is, times itself. Foiling is necessary, in which you end up with, first, 5x. Outside, inside are the same, but there's 2 of them, so negative 2 root 5x. And then last, of course, positive 1. Turns out these actually subtract very nicely, so you're left with the following after subtracting 3x technically as well. 2 root 5x equals 2x. And then they'd also divide it by negative technically to get that to be a positive. Or frankly, you could do it the other way around where you just add 2 root 5x to the left, and subtract 3x. It looks like that's what they did. Anyways, you're balancing your equation, but look, you still have another root to deal with. So dividing by 2 leads to x. And then yet again, you're going to have to square both sides of this equation. Kind of a tedious thing, but watch. It ends up actually being pretty nice. Square root of 5x squared is 5x. X quantity squared, of course, is x squared. Subtract 5x over. They kind of flipped it on you here. So x squared minus 5x equals 0. This is a quadratic that you can factor, simply noting the GCF of x. You're left then with x minus 5. Setting that equal to 0, that doesn't work. As you'll find here in a moment. Setting that equal to 0, this does work, as you're about to find again. So 5 is the answer, but why is 0, as I'm saying here, not the answer? We call it an extraneous root, but why? Well, if we plug in 5, I'll go to the one that does work, into the original problem. So we have the square root of 3 times 5 and then plus 1. And then does that equal, on the other side of the equation, if you plugged in 5 here, or pardon, 5. 5 times 5, obviously 25, square root of which is 5. 5 minus 1, of course, is 4. So that's how they get that quantity. Turns out that this quantity does in fact work out where it's the square root of 16, which is 4. And on the other side, it looks like they've done that separately. I can see kind of their breakup here. I usually like to see it with question marks, left side versus right side, but they actually just simply said, here's the left side, and it equals 4. And here's the right side of the original equation, and that also equals 4. That's an equally good approach to check your answer. 5 is a solution. Real quick, there is a little bit of a typo. It looks like here they mistyped in here 0 as opposed to 5. 0, though, will work out in the last kind of process here of checking. It will work out, I should say, to where it doesn't end up being a solution. Watch, if you plug in 0, the square root of 3 times 0, that's 0. Plus 1, of course, is 1. Great. But what if you plugged it into the right side of the equation? The square root of 5 times 0, again 0, but minus 1 is negative 1, not positive 1. Because these two numbers are not the same, 0 is not a solution. You should and should be able to graph this as well, I'll say. If you graph this as y1 and this is y2, you'll find that it doesn't work. The only solution ends up being simply 5. Okay. Now I do have several problems for us to take a look at, possibly, of which I'll probably only have time to point out a couple here on this page. On the next page, there are some things that we will be talking about in class live, but the example in particular I do want you to take a look at on your own. Let's get through some of these. So solve each equation again. Number 1, if I want to get x by itself, simply we'll subtract 3. So we have 2. And then we'll divide by, as it turns out, 2 to get 1. Because we're trying to get, in this particular problem, x by itself, and because the square root is actually not around the x, so this is a bit of an anomaly. I wonder if that was their intention. Anyways, if you go ahead and divide both sides by root 3, you end up with x equals 1 over root 3, and you can rationalize as such, multiplying numerator and denominator by root 3. So this ends up being root 3 all over 3, and that is your final answer. As far as checking your answer goes, I will go ahead and get Desmos up and running here, because Desmos, as you know, is a fantastic tool that allows us to see very quickly oftentimes if our answer is one thing or another, and of course in this case you do need to check your answer. So I'll go ahead and get Desmos ready possibly for our next question or two. So number 3, I'm going to jump to that. I'm going to ask, though, that you take a look at numbers 2, really anything that's circled in green, possibly on your own. If I do get through all the problems circled in red, that'd be fantastic with the time that we have. Number 3, 8 plus the square root of x plus 1 equals 2. Subtract 8, so you have negative 6. And then square both sides. So what happens here is when you square both sides, nicely you'll be left with x plus 1. However, the right side is 36, subtracting 1 gives us 35. Now I say however, as it turns out here, this negative 6, before you even squared both sides, should be an indicator that when you square root something and getting a negative result will not work. Okay, so I'm going to check my answer. Is 35 a solution? Well, we could plug it in here. Let's see. 35 plus 1, that's 36. The square root of 36, that's 6. 6 plus 8 is not equal to 2. 6 plus 8, of course, is 14. So I'm going to go ahead and graph this. I'm going to pull this in. I do highly recommend that we take a look at this just from the simple standpoint of relating to really every problem, but also how quickly you can check on Desmos. So here we go. Let's type in the left side of the equation as y equals 8 plus, and then the square root of x plus 1. You could also use your graphing calculator for this. I would then say y1 and y2. So there's your first equation. Your second equation, y equals 2. So then the question begs, if you just looked at the picture here, the graph, pardon, do these two functions intersect? And specifically when x equals 35, where's 35? So if you look at this, 35 is roughly here, All right, and it turns out that it equals 2, obviously, on this function. It's always going to be 2 as a y value. But on the other function, you don't get anywhere near that. You get, obviously, like I said, 14. So if you plug in 35, you get 2 on one and 14 on the other, which are not equal. If the two functions intersect, then you know you did the problem correctly. I do want to highlight, though, on the example up above, while I'm here, why don't we just go ahead and quickly see that this shouldn't work, at least for one of the answers we ended up with, as we already know. So the square root of 3x plus 1, if you recall, was the left side of the equation, while the right side of the equation was the square root of 5x. And then we said, of course, minus 1. Do these two functions intersect, and if so, where? Well, x equals 5. And we knew that because, again, plugging in 5 yields 4 on both sides of the equation, so that's not a surprise. The answer that didn't work, remember, on example 2 was 0. As you look at this, let's plug in 0 for both functions and see what it ends up being. And I think you could all see here that clearly the only solution that intersects, of which we saw was 5, is a solution, while at 0 on one and 0 on the other, we have two different y values. If the y values are different, as expected, actually the y value, is there. As expected, these two are different, 1 and negative 1, and therefore it is not a solution. 0 is definitely not going to work. Okay, so let's continue. I do know that it will be nice to graph to check on some of these. We'll see what time permits here. So as we continue, we'll take a look at number 4. Number 4, simply add 4 to both sides to get 10. Square both sides to get 5 minus x equals 100. Subtract 5 and then divide by a negative. Or you can add x and subtract 100 simply to get negative 95. It turns out negative 95 is a good solution. It works. You can check that, and I encourage you to do that either algebraically or on Desmos. Number 5, 12 plus the square root of 2x minus 1 equals 4. I subtracted 12 to get negative 8. This should trigger something, though, as you look at it, trigger something to where you notice, well, heck, if I take the square root of something, how am I going to get a negative number? Okay, remember, the only time we're technically able to get a negative answer with a square root problem is if it's a quadratic equation that you're square rooting both sides. Okay, you're not square rooting both sides of this equation. It's already square rooted first here, and there's really nothing on the other side square rooted. Not that that would matter, but you're not solving a quadratic. You're solving a square root, technically. Okay, so square both sides, like I said, 64 is the result. So 2x minus 1 equals that. Add 1, divide by 2, and you get 65 halves. 65 halves, let's just plug it in to see what that ends up being. 65 halves times 2, that's 65, the 2's divide. 65 then minus 1 is 64. The square root of 64, of course, is 8. 8 plus 12 is 20, and 20 does not equal 4. So the square root of, the original problem, which is a square root equation, of course, has an answer that doesn't work. There is no solution to this problem, just like number 3. Unlike, though, number 2, or example 2, up above, one answer didn't work, but one did. So there will be moments possibly where one works and one doesn't, or the only answer you get, of course, doesn't work, so no solution, like we saw again on those two. All right, number 8. As it turns out, actually I'm going to jump to number 12, and on number 12, just like number 10 in a sense, you're going to have to do the reciprocal on both sides as far as the exponent is concerned. If you look ahead at number 10, I do want you to try this. You'll notice that it's a cube root, so you're going to have to cube both sides. On this problem, it's actually a square root. Even though it's written as a half, you're going to square both sides because it is a square root if you think about it, which is going to undo that half as such, 9x minus 11. On the right side, you're going to have to FOIL, and here's the quadratic. It gets a little bit more interesting, as you can see, subtracting 9x, adding 11. It does end up to where you get a quadratic that is factorable, and it factors as such, x minus 3 and then x minus 4, set them both equal to 0. The two solutions to this problem do in fact work, and I implore you to try to see if it works. All of those other problems that we didn't get a chance to do, both red and green, please try and check your answer via Desmos.